So today I'm going to be taking a look at the problem enumerate all sequences of Ti from 1 to 6 such that the symmetric group S3 is given as the set of products of these elements T1, T2 in this way. And each Ti is of order 2. So right away we notice that there are 6 of these products and S3 has size 6. So we can't afford any redundancy. Oh, sorry. We also want this last one to be the identity. So we have 6 products, 6 elements in S3, so we can't afford any redundancy. Each Ti being of order 2 tells us immediately that it's a transposition, because in S3, of the 6 elements, only 3 are of order 2, and those are exactly the transpositions. So we can sort of approach this in the following way, which I think is quite nice. We can draw the elements of S3 as vertices of a graph. So let's write the elements as so. And I'll write the ones which are even on the right and the ones which are odd on the left. Now I'll draw in edges which correspond to right multiplication by transposition. So we've said there's 3 transpositions in S3. And note that if you multiply on the right by transposition, or on the left for that matter, you go from the left. If you start on the left where you're odd, you go to the right, just by definition of parity. If you start on the right, you'll go to the left. And since there's 3 transpositions and no 2, so if you multiply by a different transposition, you can't get the same thing. What we see is that there's 3 edges going from each of these nodes on the left to the right. And there's 3 edges coming back from the right to each node on the left. So a priori, it's a directed graph. But since there's an edge in each direction between any of these nodes on the left and any node on the right, I'm not going to draw the directions. So basically what we have here is a bipartite graph. We have 2 parts, the odd permutations and the even permutations, and anything on the right, which is even, is connected to anything else on the left. But nothing on the right is connected to anything else on the right. So now our question reduces to, we want a path in this graph. Well, we can rephrase it in this way. So you can start at E and then follow some edge to one of these transpositions. So that's T1. T2 is a choice of one of these edges, going back to the right. And then T3, we're visiting some new point. So at each point, the place we go is the new product of all our transpositions. And what we want is cycles in this graph which touch every vertex exactly once. So well, this is not too hard to answer. Well, okay, sorry. We want paths which touch every vertex once, but also start and end at the identity element. So identity element is in some sense special. So let's redraw the graph like this. Here's our 6 vertices. Let's maybe make this one blue, so you can tell it's distinguished. And then we want a path. So for example, one path might go like this. And that's fine, but we want all the paths. So we might ask, how can you get all the paths? And the answer is that because this is a complete bipartite graph with only this one distinguished point, the identity, these 3 points here have a action of the symmetric group on 3 letters, which is free and transitive. So transitive means well, so let's not say transitive yet. It's free, meaning if we act on any path by this action which just permutes some of these points in the way specified by this element of S3, then we cannot get back the same path unless it's the identity element. And the same thing here, we have an action of S2. So altogether, we have an action of S3 times S2. And this action is free on the space of paths. And it's transitive because if you have any path, you can just rearrange the points on the left and on the right to get it into the form of the path we've drawn here. So think about that for a second if that doesn't make sense. So this is some group. And what we see is that elements of this group will ultimately correspond to sequences of the tau I that we were looking for. So if you want to know, so this gives an enumeration. But also, I mean, just if we just are interested in the number of such things, we can look at the size of this, which is 3 factorial times 2, which is 12. So there you have it. Hope that helps.